Good afternoon. So today we're going to talk about the heat equation. So we're going to derive the heat equation first in one variable and then in 3 dimensions. That part is semi-optional. I'll talk about that when the time comes. But I want to point out that we need to take our sweet time to go over this first in order to make sure you understand later how you establish boundary conditions and how you go from a word problem to an actual equation that describes that problem. So once again, it's very, very important to not rush this. Pause as many times as you need. And after you go over my presentation, just look at the corresponding description in the book and try to understand that as well, and then compare the two, because I purposely do it a little bit differently just to simplify some things, but also to give you a different perspective on how you derive this equation. Surprisingly, there's a lot of time that you need, maybe a lecture time class, to actually explain how the equation comes to be. Because I mean, the equation itself is very simple, at least in one dimension. Once you're gonna memorize it by heart without even trying, because we're gonna solve this equation in various contexts. But the way to explain it, it's actually can't really be simplified into, just a phrase or two. I mean, if you want to understand it. So what I'm going to do is basically compromise between math rigor and enough detail actually to understand what's behind the equation itself. And so for that reason, we need to talk about physics a little bit, about some physical properties, so we can understand how the equation comes to be. And let's start with a one-dimensional case. So the derivation of heat equation, let's add here in one dimension first. Now, what is the type of object suitable for this type of equation? Well, the object that you're looking for in terms of modeling its temperature will be, let's say, a thin bar or slab, as the book mentioned, meaning that the thickness is negligible. And where the location, I mean the position in the object is given by just one spatial coordinate. So let's say the length is L. So that means the temperature at a given time point and location x is given by two variables. So u of xt, the meaning of u of xt, which will be the dependent variable of the PDE, is the temperature at location x and time t. So I'm going to use this word often, this location, so that we can distinguish it between the time variable. There is always a time variable because we build a dynamical system, right, in which we're looking at how the temperature changes in time, but the temperature this time depends on the location in the object. That's why we need PDEs in the first place. And the reason is because the nature of the material may be different from one point to another, which affects the conduction of the heat flow and so on and so forth. And in fact, we're going to enumerate a couple of physical quantities that are relevant for our discussion here. One thing I want to point out, because the object is one-dimensional, we can make some convention about positive flow and negative flow. So the temperature changes because there is a heat transfer between two objects. So you can think in terms of heat as the change in temperature of a unit of volume, let's say, caused by heat transfer at that location in the form of heat energy. So if you want a very intuitive understanding of this idea, if you imagine, for example, a piece of the material, just a tiny dot here, just a tiny point, if this point here will change its temperature in a certain amount of time, so if there is a change in temperature, either up or down, That's because there's a change in the heat flow in and heat flow out. So imagine this tiny point as a closed object, essentially, as a unit of volume, closed, and it allows the temperature, the heat flow, the heat energy to penetrate, so it can gain heat energy from the exterior and it can lose heat energy to the exterior. The difference between the two will result in the change in temperature up or down, depending on whether the heat flow in is greater as opposed to the heat flow out. So really imagine essentially the process as the heat being this stuff that is basically added and subtracted to a piece of the material. And this adding and subtraction around the location during a certain amount of time results in a change in the temperature. Because in fact, you will see the heat equation, the way you formulate it is to write essentially this change in temperature in two ways. The gain of heat energy essentially, or the gain in temperature at that location in time t, which has to be equal to the difference between how much heat flowed in that object minus how much heat flowed out. All right, so like I said, patiently, right? We have to go step by step until we get to the actual equation. So before we do that, let's actually write down a couple of important quantities that depend on location, basically on the space, on the location on the object. In the 3D case, of course, it depends on 3 coordinates in space, but now we're in the one-dimensional case, so we're gonna restrict ourselves just to one variable. So we're gonna have, first of all, one quantity which is related to the nature of the material. So we can have the density of the object at that point. So this will be delta x. This will be the density of the bar of the material of the object at location x. Remember, x is the spatial location, which denotes the position on that bar. So remember, the density is essentially in the unit of mass divided by the volume, or it's defined as the mass over a volume. There's another physical quantity which depends on the nature of the material. It's the so-called, is denoted by sigma of x, is the so-called specific heat. And this is basically the heat energy needed to raise the temperature of a unit of mass by 1 degree. So how much basically, and again, it's depending on the nature of the material, the chemistry of the material if you want. Another important term which is denoted by big K of x is the thermal conductivity, or the thermal conductivity, or the conduction term. As the name suggests, it measures basically how much the material is basically allowing the heat to flow. Basically has to do with insulation or the lack of the insulation of a material. So how much heat transfer is allowed by the nature of the material. And you can write it basically as meaning that the ability, basically it measures or it indicates the ability of the material to conduct heat. All right, so having defined these physical constants, let's talk about some convention we make about how heat flows from one direction to another. So let's write again that object, which again for convenience, imagine it's placed on the x-axis basically, right? So that means this is 0, this is L, the length of the object, and therefore the domain of the spatial coordinate x is between 0 and L. So by convention, again, very important to establish this from the beginning, imagine that if the heat flows from left to right, this is the positive direction, so positive flow. And if the heat flows from left to right, that's negative flow. So basically the way heat flows is because of the difference between temperature of two nearby points. So let's establish a very simple concept in terms of how heat flows with respect to how temperature changes. So let's say in the x-axis here, we have two nearby points, let's say x1 and x2. And let's say at point x1, you have, let's say, 5 degrees. And by the way, suppose that x1 and x2 are very close. In the limit, it's going to be basically like a small infinitesimal distance between the two. So let's say you have 5 degrees at x1 and 10 degrees at x2. Now notice that, remember, the heat flows from hot to cold point. So you always have a flow of the heat from a hot position for a hot location to cold location. So obviously if this is 5 degrees and this is 10 degrees, then the heat of the flow, the flow of the heat is from right to left. But obviously the temperature increases from x1 to x2. So the temperature increases from x1 to x2. So my point is that the change in the temperature basically is going to be always in the opposite direction to the flow of the heat. So the change in temperature from two locations. I'm talking about the change from one location to another, not with respect to the time t. And of course, consequently, if you had, for example, at location x1, let's say 10 degrees and the location x2 5 degrees, then in this case, the flow will be from right to left. But obviously the temperature will be decreasing, so the flow will be positive. Here the flow will be negative by convention. The flow will be positive, and the temperature decreases from x1 to x2. One terminology that we're going to use here is that the change of the temperature from one location to another is called the temperature gradient. In our notation, remember, U of xt is the temperature at location x and time t. So therefore, partial x with respect to xt, so the partial derivative with respect to x, will be the temperature gradient. So this remark that I made here is that the flow of the heat will be positive, namely from left to right, if the temperature gradient at that point is negative, right? So the temperature decreases from left to right. That means the flow is positive also from left to right. Okay, so basically we, like I said, by convention, the positive flow is from left to right in the one-dimensional case. And vice versa, the flow will be negative from right to left if the temperature gradient is positive. So make sure you pause it for a moment and try to visualize, because this should make sense, because everybody know how the temperature changes from hot to cold, then the direction of the heat flow. And make sure you understand again the meaning of the temperature gradient. It's simply the difference of the temperature as you move from one location to a nearby location. Because we light this object from over the x-axis, the positive is the movement to the right hand side. So when we say the temperature increases, is because as x1 changes to x2, I mean to a nearby point on the right, the temperature increases because the numbers increase to the right hand side on the x-axis. So that in that case, of course, the flow is negative. So we made this discussion to understand the minus sign in one of the important physics laws, which basically are one of the main ingredients to building up the heat equation later. So there's something called in physics the Fourier law of heat conduction. So first of all, we have one more definition here. The notation for the so-called flux, heat flux, denoted by phi of xt. This is going to be, by definition, the flow of heat energy per unit of area per unit of time. So you really imagine this like a fluid, basically. So if you imagine, for instance, the surface of an object, the flux essentially is the amount of heat energy that penetrates the membrane or the boundary of that object. But it's given per unit of area. So if you want to find the total flux, of course, you have to add up all these fluxes for the entire surface of the object. So how much heat energy flows per unit of time, per unit of area. The Fourier law of heat conduction simply states that the flux at location x and time t is going to be proportional with the temperature gradient. The concept of proportionality is going to be that conduction term, which we defined it previously in the previous page, and that depends on the location, and the temperature gradient being the partial derivative with respect to x. So again, the minus sign is because of what we just talked about here. The direction of the flux, of how the flux energy flows left and right, is always opposite to the temperature gradient, to whether the temperature drops or increases at that location. You can drop if you want, well, we're not going to drop it for now. Later on we can drop the x and t if there's no risk of confusion, but for now let's keep it general like that. Alright, so the flux is going to be minus k of x times partial x of x and t. All right, so this will be used basically deriving, like I said before, on the next page, the heat equation for in one dimension. So stay tuned for getting to that part on the next page. All right, so write down again the Fourier laws of law of heat conduction, and take a moment to write down this object. Like I said before, we can take the thickness to be negligible, or we can just take the thickness to be constant. I mean, because like a cylindrical object or constant cross section basically. But again, under the assumption that the temperature just varies with the location from left to right and not across the cross section. But that cross section area you will see is going to cancel in the end. But for now, we'll just denote it by a variable. So let's summarize again what we just mentioned in the previous page. Just to make it clear, this isn't the PDE. We're going to use this to build our PDE. The goal again is to find an equation which describes completely the temperature of the object at location x and time t. So we need a PDE in u of xt. This, what you see here, is not going to be a PDE in neither of these, because we have two distinct variables here, right? We have the temperature partial x of the temperature on the right, and of course the flux on the left side. What I want you to imagine is that this location here at x and x plus dx is very tiny. We exaggerate the distance between x and x plus dx just to visualize it. But imagine this is basically a unit of volume, a small unit of volume. And we're going to write essentially the PDE by writing essentially how the temperature changes in two ways. So think again of this portion between x and x plus dx as a single closed unit of volume, and basically we can write what happens at this location in two different ways. So let's write it in words here. So at that location we can say that the change in heat energy, the total amount of energy in terms of the, because the heat energy is proportional to the change in temperature. So the change in heat energy at location x and time t is equal to the heat that flows in minus heat that flows out. So really think about the change in temperature as a transfer of energy inside and outside the object. If there is a net gain in energy at that point or net loss, then the temperature changes at that point. So the left side of the equation will be essentially the change in heat energy at that location. And on the right hand side, we're going to write the same thing, but in terms of what comes in and out, because the difference between the two should be the amount of heat energy that is left in the object. So notice that if I take partial t of u, so u partial t of xt, this is the change in temperature at time t and location x. All right, so let's remember now those physical constants that we talked about. So first of all, we had the density delta x, right? So remember the density times the volume is the mass. So the mass of these small object is the density times the volume. So I can denote the density by, remember the notation was delta x, the density at location x. And let's denote, I forgot to mention here, let's say A is the cross-section area. So that means the volume of that piece will be the area of the cross-section, let's say A, which is a constant in the way I shape this object. And dx will be the little change, the little space change between x and the nearby point. So dx will be the height, if you want, of that object. So this will be the mass. Now, remember the specific heat is sigma of x. So when I look at the product, sigma of x, that's the specific heat. And multiplied by the volume, the mass, this will be the mass, right? The volume times the density. This is basically the amount of energy needed to raise the temperature to 1 degree. Specific heat is the amount of energy per unit of mass. So this is how much you need in terms of energy, sigma of x, to raise the temperature or to change the temperature by 1 unit per unit of mass. So when I multiply by the total mass, this is the amount of energy needed for that object to increase or decrease by 1 degree. But the overall change, the amount of degrees, if you want, in the temperature change is given by partial t. So partial t is going to be the temperature change overall. So imagine, for example, that partial t is 10. What I just wrote here is the amount of energy necessary to change it by 1 degree. We know that it's changed in reality by u partial t, because that's the meaning of u partial t. So therefore, the full left-hand side is going to be this times u partial t. So once again, all these coefficients in front of u partial t is the amount of heat energy needed to make a change of 1 degree. U partial t is the amount of actual change at partial t at that location and time t. So change in heat energy at location x and time t for that object is given by this product: specific heat, the mass, which is itself a product of density, volume, and because it's a tiny amount of volume, dx is involved there because that's going to be essentially the length of that piece. So on the right hand side, we're going to have the heat flow in minus heat flow out. So imagine, for example, that there is heat flowing in from the left side and heat flowing out from the right hand side. The difference of the two is responsible for raising the temperature given by the left hand side. So on the right hand side, I'm going to have the flux at location x and time t. Remember, this is also per unit of area, so I have to multiply it by area as well, minus the flux at the nearby location, x plus dx, same time t, and the cross-section area is the same. So notice that whether you call that the cross-section is the same and the temperature doesn't depend on the cross-section, or you can say it's of negligible thickness, under our assumptions here, the cross-section area cancels from left to right. At this moment, on the right-hand side, we're going to replace the flux with its equivalent given by the Fourier law of heat conduction. So here we're going to have minus k of x partial x at the point xt minus, raise a parenthesis, open a parenthesis here, phi of x plus dxt, that's going to be minus k of x plus dx, and then u partial x at x plus dx and t. All right, so let's move these terms a little bit. And here minus minus is plus, so I'm going to start with the last term. Ux, x plus dx, and t minus k of x, ux, u partial x, u of xt. All right, so let's divide by dx both sides and pay attention what we get on the right-hand side, as basically dx goes to 0, because essentially we want to write this for a tiny point on the material, you know, when those two locations are essentially the same point. So k x plus dx ux x plus dxt over dx. So if you look carefully, this is a difference quotient for the function k of x ux xt. So look carefully here. Basically, t is the same, it doesn't change, but on the left, on the first term here, we have x plus dx, and this is just x. This is like a difference quotient. You could have actually replaced dx with h if you want, but as dx goes to 0, what you have on the right-hand side is basically partial x of the product between k of x and u partial x of xt. So partial x again. We're going to do more simplifying assumptions before we move on with the actual one-dimensional heat equation. But let's not rush this. Let's just summarize one more time. Left side is basically the amount of heat energy that results from a change in temperature at time t. That's basically given by partial u with respect to t. What's left on the left side are just physical constants that are involved in that process, specific heat, density, and so on. The right-hand side expresses the same thing, but as energy coming in and out on that unit of volume. That happens to be essentially a derivative with respect to x of the product between the conduction term, k of x, and the temperature gradient, u partial x. Because it's still too complicated to solve in the beginning, now we make other simplifying assumptions. We're gonna assume that the specific heat, the density, and finally the conduction term are constant, independent on the location. So basically sigma of x is equal to sigma, delta of x is equal to delta, k of x is equal to k. And if that's the case, then this k of x, if it's a constant, pops out of this derivative. So you're left with sigma delta u partial t equals big K u partial x twice. So let's write it down on a second page. All right, so the equation becomes now sigma delta u partial t, like I said, of u of x t equals some constant, that heat conduction term, big K u partial x twice of little xt. All right, so these physical constants can be brought up into one place. And for convenience, remember, if there is no risk of confusion, we can replace u of xt with u. We don't have to write u of xt all the time. So on the left, you have u partial t equals big K over sigma times delta, and then u partial x twice. Yet for even more convenience, if we don't need to refer to these physical constants individually, we can replace this with another constant. Renotation. For instance, u partial t equals a squared, u partial x twice. That's another convenient thing in many applications, because this constant is positive for a reason that you will see later. Might be convenient to write that constant in form of a squared. But it doesn't have to. I mean, in some books you have, for example, little k of uxx, not to be confused with big K, the conduction term. So that's another version of the of how you write the heat equation. So yeah, I mean, in fact, we can use this format because it's consistent to many problems that I assigned for the homework. Little k, right, being the positive constant that comes from these three physical constants. So you notice that there are plenty of simplifying assumptions, because the heat equation is quite complicated if you leave it as general as possible. So if you leave all of these physical constants depending on the location, on the space variable x, it's a quite complicated equation. If you make the simplifying notations, simplifying assumptions, then this is the simplest possible form of the heat equation. U partial t equals k u partial x twice. And what's important from this point on, again, is to remember, first of all, where it came from, because many boundary conditions are still given in terms of the flux. We'll talk about how we establish boundary conditions later in another lecture. So make sure you remember this formula as well. In addition to the actual heat equation in one dimension. So that's it for today. In the next lecture, I'm going to derive the heat equation in 3 dimensions and as an application of calculus 3 things. And then after that, we're going to have at least 2 lectures on simply stating the problems in various conditions and how to set up those boundary conditions in terms of these variables. So that's it for today.